Okay, welcome back. Today we are going to be talking about software quality, and this is very different from what you have already discussed in this course as part of quality management of the process of producing software. So there are two things here, the process and the product, and quality measurements, quality monitoring and quality improvement can be applied to both of these. So for example, you can make process improvements, and the CMM metric suite that exists actually covers how do you measure the process's efficiencies, how do you improve the process efficiencies, and so on. Whereas there is also an aspect to be considered in terms of producing quality software, and that aspect is that of the quality of software itself, inherent to the design techniques that we use, the kind of abstractions that we use within building software, and so on, and that's going to be the focus of today's discussion. And all of this is motivated by taking a perspective on the changes that have happened in software, and actually the statistics about software development projects themselves over the last 20 to 30 years. So if you take a look at this graph, I mean this chart here, what this is basically trying to show is that even though a lot of things have changed about computers and software, basically there are some characteristics of software projects that have remained constant, which is that 35 years ago or 40 years ago, software projects used to be constantly late, that they were never on time, they were never under budget, on budget or under budget, they were always over budget. They were very buggy in the sense that they had a lot of correctness issues with the software itself, and they were very inflexible. So every time we had to make a small change to the software, it would cost a lot of money, it would cost a lot of time, a lot of effort, a lot of people got involved in this, and this characteristic of software has not changed even as late as the 2000 when this survey was done. And essentially when they did the survey of software projects in the late 80s, they came up with a term called the software crisis. And the software crisis was basically meant to illustrate the fact that the average software projects was late by an average of almost 30 months, which was quite long. In fact, today's projects don't even last 30 months as a whole. And the cost of software overall, the total cost of ownership of software, more than 70% of that cost was taken up by maintenance, which means that finding a bug and figuring it out and correcting the defect in the software, as well as making small changes because of incremental requirements, was very expensive. And there were certain factors that we are going to go into today as to why that was so. And the quality of the software itself was quite pathetic, in the sense that there were a lot of problems and issues with the software. There were a lot of stability issues, there were a lot of ease of use issues, there were maintenance issues, there were performance issues, and there were just functional correctness issues, that it would not conform to the specifications that were written out when this entire project was started. So some more perspective on the software crisis. In fact, in taking a survey of the US defense projects in the 80s, they kind of broke it up into several categories. One were the really large projects, which was over $2.5 million overall. Most of these were not delivered at all. Over 85 to 90% of these projects eventually were not delivered, and they became so late that the projects got canned, or they got cancelled. Right? The second class of projects, which are slightly smaller than these, were delivered, but they were never used, and they were never used because of various reasons. The quality of the software was a major reason amongst them. And then if you go down, you see that some of these projects were completely abandoned or had to be reworked from scratch. The next category of projects, which fell into the $1.5 million to $2 million range, pretty much had to be reworked from scratch because they did not conform to the specifications. It took so long that the requirements had now changed in the meanwhile, and so on. And it was noticed that only the very small projects, relatively small by those standards, were used because they fit the requirements and appropriately, and they were still significantly over budget, though nothing was ever delivered on time and under budget in those days. So experiences such as this essentially gave rise to the term the software crisis, and people were wondering as to what were the causes behind the lack of quality within software. And in fact, as a humorous aside, Brian Russell has come up with these laws of software relativity, as he calls them. Again, these are not laws, these are just, it's a humorous aside, but it kind of illustrates the point that he's trying to make about software. The first thing says that as the software project approaches release, the mass increases, that is the number of people that end up becoming a part of the project goes up dramatically. The energy required to release the software project is inversely proportional to the time before a scheduled release, and so on. You can read the rest of these on the screen, but what these are basically trying to put in perspective is the software crisis that was occurring in the 80s, that every time the project got delayed, a lot of the people got put onto it, so there were manpower issues on this, and that was not the way to solve this. Like Fred Brooks also said in the late 80s, adding people to a late project is only going to make it later. So what are the properties of failing software? It's worthwhile to take a look at some of the causes that led to these kinds of failures, that led to the poor quality of the software that was being produced in those days. And one of the first thing that comes up in this list is redundancy. What does this mean? Redundancy is basically referring to the fact that in a software project, most of the code or the development takes place from scratch, and there is very little reuse of components that are taking place. Right? What this essentially, how this affects quality? Every time you write code, it has to be tested thoroughly, and the number of testing combinations that are going to exist depending on the number of inputs, parameters that that module is going to take, it tends to be prohibitively large. As a result of which, unless either statistical testing techniques are employed or the software is not very well tested. Now, if we had reuse and we were using pre-built components that have been used in production situations several times before, then you could be reasonably sure that these components could handle whatever is going to be thrown at them, because they had not just been tested, but they had also been used in other applications. But that doesn't happen very often in software. There is a very high degree of interconnectedness between the modules. So this leads to what a term called fragility of software. And fragility basically refers to the fact that a small change that needs to be made is going to end up costing a lot in terms of time, in terms of effort, in terms of money. That is because of the high degree of coupling that exists between the so-called modules within the software. Typically, a well modularized piece of software is supposed to have a very low degree of coupling between these two, as we shall see going forward. And one of the reasons why maintenance was so hard and it took so long to fix an issue or to add a certain requirement was the low understandability. So the low understandability of software came about because of a couple of reasons. One was that the abstractions were simply not there within the code. So there was lack of encapsulation. There was spaghetti code all over the place. Procedural abstractions were being used. And procedural abstractions basically consisted of a set of functions, a set of global data that these set of functions manipulated, and that just was not going to cut it as far as a second programmer who did not write the original piece of code trying to understand, make sense of this spaghetti code, and now he had to make changes in this environment. And of course, documentation was always obsolete because the software was changing much faster and the processes were not being followed. But that's not a focus of our talk here today. And lastly, there were human factors. The human factors was manpower estimation was grossly inadequate. There were no effort estimation techniques, but those are things that you have already seen so far in the course in terms of how to attack the process, how to deal with manpower estimation, how to deal with effort estimation of modules, and so on. Again, that's the last bullet is something that we are not really going to get into in this particular lecture. So what happened was, these properties, so the common error in managing the process of software development is well illustrated by this chart. What this is trying to show is that on the x-axis is the functionality that is being added, and on the y-axis is the quality properties of software. So things like robustness of software, things like the unit testing of software, things like correctness, things like performance, and so on. These are the quality, the non-functional requirements, so to speak. Now, as a project went on, suppose there were early releases before the project actually completed, and these points indicate early releases. What normally happened was a lot of functionality was added initially, all the way up to the point that the project came to its close, and then all the testing and the debugging got done in the last part of the project. So a lot of the code was added without adequate testing getting done, without adequate attention being paid to performance, paid to ease of use, being paid to structural integrity of the software and so on. And then most of the debugging took place in the last phase. Whereas what is actually desired, right, is something that will set up the quality framework very early in the process, and then you add the functionality as you go along, and you can make the same releases with the same amount of functionality, but you'll have a lot more quality to it, right, and that's the desired process. So here is another example about how lack of encapsulation hurts maintenance. Typically we've seen this chart before in terms of what is the breakdown of maintenance costs, where are most of the bugs filed, where are most of the change requests coming from, and what this shows is, and these are the only two important categories, the largest categories. The first one is a change in user requirement, and it costs the most, not because there are a lot of changes, but because every change is very expensive to handle. Because the software is fragile, it's not easily amenable to extension, it's not easily changeable or flexible. This happens, and because of lack of encapsulation and lack of abstractions, a change in the data format, this is a surprising statistic that almost 20% of the maintenance costs come from changes in data formats taking place, and the Y2K bug is a famous example or infamous example of this. So what are the quality factors in software that we need to be watching out for? The quality factors can be divided into two main categories. One is external, external implying that it is visible to the user. Obvious example of this is performance. So if a software is slow, it is easily perceived by the user. Ease of use is another example of this. And the other factors are driven by internal needs, such as robustness of design. So if I want to add a feature to the software, what is it going to cost me to do? That is driven by the robustness of design. Is the design flexible? Is the design open? Is this software portable to other platforms, and so on? The documentation of the code, etc. So what building quality software, the process, the mindset is all about, is about thinking about the internal factors and focusing on the internal factors in order to ensure that the external quality factors are being met, because it's only the structural software with structural integrity that is going to allow you to make these changes quickly. It's going to allow you to give the kind of performance that the user is going to expect of the software. So it also can be thought of as functional properties of software, such as profit, customer orientation, etc., versus the structural properties of software, which basically lead towards cost reduction. So if we take a look at that, and that was a categorization of quality features, and if we actually delve into the quality factors themselves, correctness appears at the top of the list, as is to be expected. And what is correctness? Correctness has to do with the fact that the software as has been built conforms to the specifications, the requirements that were laid out in the beginning of the process, right? So it's a means of means of ensuring correctness are testing and debugging. That's a straightforward means. The other one is layering or architectural approaches towards ensuring correctness, so that changes in the lower layers essentially don't affect. They only affect the layer that is sitting on top of it. So for example, when you change the operating system platform, if the software at which manages, say, functional needs of, say, inventory management is not isolated from the operating system layer, then you would have to make changes throughout the software, and the more change to the code that is being made, the more perturbation that is being caused within the system, the more likely that there is going to be a quality problem in the software in the near future. The next quality factor that is very, very important is robustness, and robustness basically correctness refers to the fact that the software performs correctly under certain conditions, so it meets the specifications, and robustness refers to the ability of the software to deal with abnormal conditions, so those that were not specified, for example, or they might have been specified. And correctness and robustness, when put together, produce reliable software at the end of the day, and so these are factors that we should focus on. But however, there are other factors as well that we would do well to take into account, and these are some of these are expressed here. Extendability of the software. So the extendability is the ability to not necessarily change a system, but add to a system. So for example, we were now building a module of inventory management, but we would like to add to it the ability to do logistics planning, right. So, for example, you are managing inventory as well as you are going to have to manage shipments around to various warehouses. So, logistics planning has to be added to this. Now, when such a major requirement is brought into the picture, if the first piece of software, the inventory planning system, was not built right in terms of design, then it's not going to be very extensible. And extending is going to cost a lot. Maybe new technologies would have to be used, the entire system might have to be upgraded, and so on. So, the autonomy of modules strongly influences. What this really means is the degree of coupling has got to be very low, and the strength of cohesion or the degree of cohesion within a particular module has to be very high, and we will go into the details of what exactly that means in a little while in this talk. The next one is reusability of the software. So, the ability of a module to be useful in multiple scenarios or multiple situations directly is going to affect the quality of the software, right. So, this is also related to robustness, because if a module has been tested before, it has been used in multiple situations before, then it is likely that people will safely use it again, and that would lead to a reduction in cost, it will lead to an increase in quality, and so on. And modularity essentially refers to the notion of extendability and reusability. How well is it encapsulated is what we are talking about when we refer to modularity. Other factors are portability. So, the ability to execute on a wide variety of platforms. So, does this execute on Linux, on Windows, for example? Does it work with the Netscape browser as well as with the IE browser, and so on. So, that is various configurations. The ability to execute on various configurations is what portability refers to. Efficiency refers to the usage of resources. When I run this software, for example, do I need a mainframe to run it, or a smaller box with 1 or 2 CPUs is going to do? Is it a memory hog, or is 256 megabytes of memory going to be enough for this? IO, bandwidth, disk usage, etc., are all features or resources that have to be carefully conserved and managed, and is software efficient in dealing with it. The integratability factor is basically refers to compliance with standards. Now, if I buy a piece of software from one vendor, and if I buy another piece of software from another vendor, so for example, my financial or accounting system has been bought from one vendor and my inventory management system has been bought from a second vendor, will these two talk to each other? Now, every time I lose inventory, for example, I have to record it as lost inventory within the financial system that I have. So, am I able to automate this transaction? Am I able to pass data from one software to another? Am I able to pass control from one software to another, is what this refers to, and this is largely driven by compliance to standards. If both of them work off of a common standard, then integration is going to be a piece of cake. Otherwise, it is going to be very hard, taking up a lot of time and resources. Then there are certain user perceivable factors like we talked about before. Ease of use. How well have you understood your user? How easy is it to install the software is an ease of use issue. It is not just the functional ease of use that we are talking about, but the non-functional aspects of it. If it is going to take you 2 days and it is going to require an expert system administrator to come and install the software for you, then it is not going to go out very well in certain situations. Right? If it is a very complex piece of server-side software, it may be okay, but if it is a simple desktop software like a word processor, then it should be self-installable completely. How well does it support operations such as monitoring, deployment, redeployment, bringing it down, etc., versioning, etc. Then there is performance. There are certain performance guidelines or performance requirements that would have been laid out at the beginning of the process, and how well does the software conform to these performance requirements. So, response times, throughput, etc., etc. But certainly something that you have to worry about is you do not have to worry about performance unless you meet the correctness criteria. The first two criteria that we laid out, which is correctness and robustness, are absolutely key quality factors that we have to focus on. And so, the question that we tend to ask ourselves is, we have looked at all these quality factors that affect software, but what are the keys to achieving the structural quality? What is it that we can do in design? What is it that we can do in our process that will help us produce quality software? And that is the focus of today's lecture. So, the first key, and remember, one of the problems that we saw right? The first key is that of reuse, and reuse was one of the main causes why software failed. So we have to attack that by making software modules be more reusable, by having the appropriate degree of modularization or encapsulation within the software, that we can create reusable modules, by giving the confidence to the user that this module has been tested under a wide variety of conditions, that the module or the component is going to work on a wide variety of platforms, and therefore it is reusable. They don't have to develop their own piece of software for something like this. It reduces development, and we have seen all the benefits of reuse in past lectures, but the key ones are: it increases reliability, which means it is going to directly improve robustness. It reduces the development time. It takes the risk out of the process side of it as well. It's not just the software quality that gets improved, but the risk in terms of the process side of it, in terms of estimating how long a piece of software is going to take to construct, can also be brought down by reuse. And we have to distinguish between designing a piece of software by reusing components, so that is called design with reuse, and designing a component itself within your software construction process, so that it can be reused across a wide variety of situations and products, and that is called design for reuse. The second key to achieving structural quality is that of abstraction. And this is it's kind of the term is not very well defined, but we should try to put a definition to the notion of what abstraction is within software development, and there can be different levels of abstraction, and that's what in fact object orientation is all about. It's about introducing abstraction at various levels within the software design process, within the software construction process. The third key to achieving structural quality is continuity in the process. And what do we mean by this? Now we know that there are various phases in the software development life cycle, starting from requirements, going on to analysis and specification, going on to design, going on to implementation, going on to testing, and so on. Often what used to happen with software development projects of the past is that requirements used to be specified in natural language, say English. English was the common denominator for specifying software requirements. Now, it was now up to a human or a person to take this specification, understand it, to take the requirements document, understand it, and create a specification, do the process of analysis. In that result, now to see whether the analysis that had been done, the specification that had been written, conformed to the requirements that were given in the first place, it was not possible to be done by a machine. It could not be verified that the analysis was indeed correct, that the specification that had been turned out as a result of analysis could indeed be traced back to the requirements. So, if we try to pictorially put this out, there are different phases. So, the first phase is that of analysis, and in goes the requirements document, and out comes a specification, right, and the specification is then fed to a design phase, and out comes a design. Now this is fed to the implementation phase, and out comes code, right. So, there is an input to every module and an output to the module. Out comes code from implementation. The code is then fed to a testing phase, which basically verifies correctness. Now, this is the process, and in the process what happens is that there are artifacts that are created by every process, right. So, the analysis creates the artifact of specification, design creates the artifact of design, implementation creates the artifact of code, and testing basically gives you a Boolean answer as to whether something is right or wrong. Now, in the traditional software engineering process, what happens is that these artifacts that we have laid out, the specification, the design, and so on, do not get reused from step to step of the process. So, in other words, there is a human who reads the requirements document, comes up with the specification. Another human reads the specification and comes up with a design. Now, to go back and verify whether the specification meets the requirements, whether the design meets the specification, whether the code meets the design, and so in turn meets the specification and the requirements, is simply not possible, because there is lack of continuity in this process. Now, if we can somehow achieve that continuity by keeping a common language across this, that there is successive refinement going on all the way from requirement specification, analysis, design, implementation, and then testing, then we can ensure that there is traceability in this process, and that is the key, and that is what is written down here as continuity in the process. The need to maintain the continuity all the way from requirements to pass testing, right? Testing should really be taking code and taking the requirements as an input, and then with the help of a machine verification technique, you are able to now match the requirements to the code and ensure that the code indeed meets the requirements that have been written out. But that, and if we can achieve that, we would have gone a long way towards improving the quality of software that gets constructed. So, coming back into the different, so we saw that the three keys to achieving structural quality was reuse, first of all, abstraction at various levels, and continuity within the process. Now, coming back, what is abstraction? How do we define this? What are the different levels of abstraction that we have talked about, etc.? And abstraction is as the word itself implies, it's basically the process of separating out the properties that is inherent in some body from the body itself, right? An example of this could be that every vehicle is characterized by certain properties, and that's an example that is given out here. Every vehicle is characterized by certain properties. The properties of a vehicle are it has an engine, and it can move you from one place to another. Now, it's not necessary that it's going to have wheels, because not all vehicles have wheels. Land vehicles have wheels on them, and that is another feature that we would want to look at. So, if we take a look at land vehicles, then we can say that land vehicles have wheels in addition to an engine, and they have some means of steering, etc., etc. So, what we are trying to do in this process is to take a look at a specific object. So, in this case, let us say we took a look at a car, and now we are trying to generalize some properties from this specific object and then apply it to all objects of that kind. So, no matter whether you are talking about a Maruti car or whether you are talking about a Hyundai car, you will notice that it is going to have an engine, it is going to have four wheels, it is going to have four doors, etc., etc. So, these are the properties. It has doors. How many doors it has could be relevant only to the specific instance. For example, you could easily have a two-door car, right? And some properties can be fixed. Four wheels on a car is typically fixed, no matter which type of make of car you end up going towards. So, the process of abstraction is the process of more human-like reasoning, right? It's a process of generalizing from specificities. So, going from a whale to an animal, and whale to a mammal, and then to an animal, and therefore in that process what you are doing is you are taking certain essential characteristics and you are taking them away from that particular instance of the whale that you saw, or particular instance of the car that you saw, and then you are creating this abstract representation, saying I am going to stay away from this car, but I know what all cars are now characterized by. So, in other words, it can also be thought of as distinguishing essence from detail. And what is important in considering all of these definitions is that we have to somehow relate them back to the notion of software quality. Remember the factors that affect quality that we went through. There were factors such as extensibility, there were factors such as reusability, there were factors such as maintainability, understandability, and so on. Now, we have to be able to relate all of these back to that, right? And that's when it becomes important. Now, so another definition of abstraction is the notion of distinguishing essence from detail. So, what exactly does this mean? This means that what is important about it, not the representation of that, how it is constructed is something that we want to take a look at later, but what can it do for us is what we would like to take a look at first, and therefore that is called the separation of the interface from the implementation, right. So there can be different or multiple representations for a particular interface for some object or a body, and those different implementations, it now becomes possible when you separate them to replace one implementation with another. And if this level of abstraction does not exist, it becomes very difficult to change something in the software, because if the interface and implementation were intricately mixed, then the clients of that particular module would have to now be changed if that module changed as well. So abstraction focuses on the what instead of the how. The what is the process of analysis and the process of specifying the interface of a module, and the how is the process of design, where you specify how do you build that functionality the module is now exported to the rest of the world. So why is abstraction useful in producing quality software is something that we have to be convinced about before we move forward. So one of the things of separating implementation from interface is that it safeguards against implementation variations. Right. What this means is that you can essentially change the implementation of something without affecting the clients that use that particular module. A good example is the famous or the now infamous Y2K bug that existed. What happened there in that case was not, the criticality was not caused by the fact that the representation of the date simply had 2 digits to represent the year instead of 4. Although that was a problem, that was not the heart of the problem. The heart of the problem was a lack of abstraction, in that the internal implementation of the date was exposed throughout the software, and they did not use an abstract interface to a date. As a result of which, when a change had to be made to the structure of that module, the date module, it had to be changed in literally millions of places which had now used this particular internal structure directly without an abstract interface to it. Therefore, that separation of the interface from the implementation, the separating the essence from the details is very, very, very critical. Another example can be that you can construct a stack as a list or as an array, right, and it does not matter to the user of the stack as to how you end up building the stack. What he cares about is the operations that the stack supports, the pushing, the popping, the top of the stack, etc., creating and deleting a stack. And as long as you implement it using an array or a list or whatever else, it does not matter to the user of the stack. And it also promotes reuse. Abstraction will basically allow you to now say that a car is everything that a vehicle is, right, but it may have certain specific characteristics such as 4 wheels. A vehicle, a truck is also a vehicle, but it may have 8 or 10 wheels or 12 wheels. So this notion of reusing whatever definition has been done up to date, but now extending it goes a long ways towards promoting reuse as well. So it's important to try and figure out as to how we get the process of abstraction right, and there are 3 key quality characteristics that we have to look at in order to ensure that the abstractions that we have come up with are just right. The first one is be precise. So there needs to be some formal way of putting down these the characteristics, the properties of abstraction that we are trying to write down, the properties of the module that we are trying to write down. The second thing is that it should be complete, that it will not be reused unless it is complete. It has all the facets that are attached to it that could be used by various people. The third thing is that you do not have to go overboard. You should not over specify, else the understandability feature is going to get seriously affected. Right? If there are too many details that are coming out, it is not the essence of that object, it is not the essence of that body anymore. So that is what is caused by over specification, and we have to be wary and guard against that. So there are different abstraction techniques. In fact, if you take a look at this list: encapsulation, information hiding, polymorphism, inheritance, genericity, and so on, it's essentially the list that when combined makes up what is called object orientation. So object orientation, the focus of object oriented design, the focus of object orientation as a process in general is that of abstraction. How do we maintain the continuity in the process, as well as how do we provide the right tools for people to create these abstractions at the appropriate levels. and that's what it is. So let's go through some of these things in slightly greater detail and see what each one of them mean. The first one is that of encapsulation. What is encapsulation? Is also known as modularity, and the encapsulation is all about putting together data and the operations that operate on the data, directly operate on the data, and that's the key part, the last part of operating on the data. You don't want to bring together unrelated operations. You don't want to bring together operations just because they kind of sound nice or because they vaguely deal with it. They have to directly be manipulating the data that you are storing as part of that object, of that module, of that entity. So that's what makes sense. So to give an example, a class in an object oriented language provides you a means or a tool of creating an encapsulation. Now what you do with it is clearly up to you. So if you are going to create a printing service encapsulation, for example, you might have, remember we saw this printing service, and to create this module you would first say that it has some data that is associated with it, and the data could be marked down here as queue of requests, and then there are operations that manipulate this queue of requests. So the operations, the first operation could be queue a document to be printed. The second one could be remove a document from the queue. Etc. So what we've tried to do here is we have tried to create a module, a building block, an encapsulation of a piece of data, which in this case happened to be the queue of requests, and a set of operations. But it's not just any set of operations, it's the set of operations that directly end up manipulating this data, and we bring them together in a cohesive unit that cannot be taken apart. That's what encapsulation is all about. And a related principle obviously is separation of concerns. So you don't want to have too many concerns sitting in the same module. So for example, if you consider the printing service, you don't want to have more than one responsibility attached to the printing service. The printing service, for example, will not monitor your web server that is running at a site. It is a completely unrelated task, and there is no reason to bring these two things together. So this has to stick to its, so this is the, let's say this is the web server and this is your printing server, and there are two very different things, and this has the web server has the responsibility of serving web requests. The printing service has the responsibility of serving printing requests or print requests. Now if you ever combine these, it would make no sense. So the separation of concerns, drawing the line between two concepts that are completely unrelated to one another, is a part of encapsulation, is the part of making sure that only things that are related stay together but nothing more. And what this does for you is it helps manage the complexity, and the way it does that is that instead of having spaghetti of mixing all these things together, so for example, if you didn't have a means of encapsulating and separating these concerns, then all of these would sit together. There would be a bunch of data, the data related to the web server, the data that was related to the print server, and so on, and then there would be a set of functions which manipulated this global data. That's exactly the situation that you want to avoid. You want things in their own modules, you want things separate from one another. It's very now easy to understand this code. It's so the degree of understandability and the maintainability of the code goes up significantly when it is well encapsulated, and that's what this refers to. So the modules, which are the units of encapsulation or units of abstraction in this case, what are the characteristics of these modules? The modules should basically have what are called building block properties. So when you take bricks, suppose you're building a wall and you're going to do it by putting bricks on top of one another and then cementing the bricks. Now the bricks have certain essential properties being building blocks. They have well defined shapes, If the bricks were all of odd shapes, you could not possibly put them together, right? They have well defined shapes, so you know that you can stick one brick next to another. That's exactly the same thing with respect to software. They have well defined interfaces, and therefore you know that two components can come together because of these well defined interfaces. And the second property is that they are very independent, in that if I pull in a component, I don't have to pull in 10 other related components. So there is a low degree of coupling between different components, or between different modules, between different encapsulations, and that's very important. And so examples of modules in various languages can be procedural languages have subroutines, object oriented languages have classes and objects, and there can be languages like Ada, for example, which are object based but not completely object oriented, which have the notion of packages. So the desirable characteristics of modules are, we said it needs to have a low degree of coupling and a high degree of cohesion. What does it really mean? There are different levels of coupling within software that we can see, and this chart lists it in the decreasing order of strength, which means that what you want is the lowest level of coupling, right? That is data coupling. So content coupling refers to when a module directly refers to the contents of the code of another module, and this is absolutely something to be avoided, and an example of this is a jump statement. So if you write control that jumps from one place to another in the code, that jumps from one function to another in the code, then it's not very good, right? The second pretty bad degree of coupling that we have is what is called common coupling, and common coupling occurs when you have access to the same global data. Every time you have global data, then it is very hard to separate the two modules together from each other. Then there are other degrees of coupling. There is control coupling, which directly affect the control of another module without reaching in for the code. So you're making a module do something that is not its responsibility. So for example, one module is requesting another to print an error message on behalf of itself. You should be printing the error message in the first module and not sending it to another module for that to get printed. So that's an example of that. Then there is parameter coupling, which is bound to happen, right? In signatures, it's bound to happen because you're going to have to call different modules functions. So there are parameters or data that has to be passed from one module to another. But this per se, it's bound to happen. It's not an issue, but this degree of coupling is acceptable because in strongly typed programming languages, there is a type checking that is done by the compiler that tells you whether you're passing things of the wrong type, whether you're passing data of the wrong type, so that somebody else is going to manipulate it wrongly. So that cannot happen, and it's okay to do this. And then there's data coupling. So just like we had a strong or weak coupling to be a desirable characteristic, we have strong cohesion to be a desirable characteristic. And there are 6 classical levels of cohesion that we can see. One is called coincidental cohesion, which is driven by stylistic concerns, right? An example here is print prompt and check parameters. Now this is a shell, a function in a shell thing probably, and what this is trying to do is two different things. Printing the prompt and checking the parameters that have been given to it are two different functions, but they are trying to put these two together, and that may or may not make sense. It typically doesn't make sense to do things like this, which is why it is the first one. By the way, this list is in the increasing degree of strength, and you want as high a degree of cohesion as you possibly can get. The second one is logical, so related logic, but there is no corresponding relation in control or data. Again, something we don't want, a library of functions that are completely unrelated to one another, right? But they may be in a library because they all are math functions or something like that, something that you don't want again. Temporal series of actions that are related in time. Initialization is a good example of this. And then there are 4 other levels of cohesion, and what we really want is the final level of cohesion, in which there is data, it's called data cohesion, and data cohesion refers to the fact that the central item around which the module is being constructed is a piece of data, and then all the things that are surrounding the piece of data manipulate that data in some way. So it's a set of operations that are related to a single piece of data, and objects and classes and object oriented design help us do that. So typically what we want is a low degree of coupling between modules and a high degree of cohesion within a module. And there are different classical definitions of these that we have just gone over, and you should take care to ensure that your design follows some of these principles. So the third level of abstraction that we'd like to go over is called information hiding. And what information hiding refers to, and here is a definition by Wurstbrock, who was one of the people who did some pioneering work in the area of object orientation. So I'm just going to quote this first before we talk about it. Like us, objects have a private side. The private side of an object is how it does these things and can do them in any way required. How it performs the operations and computes the information is not of concern to other parts of the system. And the last sentence in this particular quote is the key, and this goes back to the notion of separating the essence from the detail, separating the what and the how it performs it. So the what is the one that is the public interface of the system, the how is the information that is private, and you have to somehow provide a tool for keeping this information private. So the implementation, for example, of a stack as a list. The list representation of the stack is to be kept private. It doesn't need to be exposed, and there needs to be some tool within the language that you're working with, within the design notation that you're working with, to ensure that this is private data, this is private representation, as opposed to a public interface that other people can see. So in a way, this is an access control mechanism, right? And that's what this slide is going to show as well, is that the interface is something that one must provide the intended user information about how to use the module correctly and nothing more, right? Just like that, the implementation refers to is the information that is needed to complete the module to the implementer, and nothing more is provided. So those two parts are kept separate. Another way of looking at it is that we keep the protocol separate from the behavior, right? The protocol is the envelope of the behavior, and the behavior typically says what is the way the object acts and reacts. So objects typically do changes of state, they send messages to other objects and so on, and the envelope of the behavior are simply the operational signatures that form part of the class definition. So the obvious advantages of information hiding are that reused abstractions become more reliable, as a result of which you want to keep the two things separate, and therefore implementation can be changed without breaking client code. Now the last abstraction that we will consider today is that of inheritance, and here is a motivating example. Suppose you want to computerize personnel records. We start by considering two types of employees, engineers and salesperson. Both of them have name, birthday and salary as attributes, right? These, remember, the essential properties, and the salesperson has one additional attribute called commission. Now how do you model something like this is the question. So one way of modeling this is to have a class employee, and the employee has the name, birth date and salary attributes attached to it, and then there is an engineer, class engineer, that you now come up with. There is a new module that extends the employee, so it reuses everything the employee has and now simply adds a thing called speciality of the engineer. Similarly, a class salesperson, which merely extends what the employee has and now extends it by adding commission, which is the additional attribute that we saw that this had to have. So this is a way of factorization and specialization. You are trying to reuse most of what's there, all of what's there, and trying to add to it the features that make something more specialized or more specific. Another way of doing that also could be by inclusion, but it's a very poor substitute for inheritance. And by the way, this notation that you just saw, which is an object notation for inheritance, basically allows you to define what are called base classes and then extend them by using the inheritance mechanism. So there is the extends keyword that is being employed in this particular case. So you can also do this with inclusion, but this is not a very good substitute for inheritance, primarily because of this reason. The benefits here of inheritance are that in the case the derived object also behaves as if it were an instance of the base class or the base object. So a salesperson is also an employee, an engineer is also an employee, and so any object of type engineer behaves as if it were an object of type employee as well. So if you wanted to call some operation saying raise salary, and the raise salary was defined on the employee, then you can call that even on an engineer or a salesperson without having to worry about it. But in the case of inclusion, you would have to expose the structure of the class, which would be a bad thing to do. You would be breaking encapsulation at this point in time, and therefore what you need to seek for is achieving subtyping inheritance, something that we don't need to go into as far as this class is concerned, but something that you learn about in design when you go ahead here. So the various uses for inheritance here are, the first one is subclassing, the second one is subtyping, and the third one is specialization. And what this is really giving you is a hierarchical, a tool for creating hierarchical abstractions. So the first level in the hierarchy in the example we saw was that of employee. So we wanted to extend the hierarchy. The second level was that of a salesperson or an engineer. Both of them were at the same level. Now you could obviously specialize that further by saying these were electrical engineers versus mechanical engineers, and maybe there is a further specialization of salespeople as well. So inheritance is also an abstraction, and the abstraction that inheritance provides is a way of creating a hierarchical abstraction. Because that helps us model the things that we see around us much better. So what we've looked at today is the features that affect the quality of software. So we've looked at both the external features as well as the internal or the structural integrity of the software types of features. And then we have seen how can we affect these features in a better way. We saw abstraction and reuse were the keys to achieving structural integrity within software. And we took a look at the various levels of abstraction, such as encapsulation, such as inheritance, such as modularity, such as information hiding, and so on, that help us achieve a certain design style that can contribute to much better quality software.